Mhm. Das gibt das Zug von Zugständen. Und selbst im nächsten Schritt ist es. Schon wieder super.
Doesn't look bad, yeah. Let's discuss it a little bit. So you start your initial guess of what the winning region could be with the set of core states from which we can enforce to reach F in the next step. Let's see what this would mean for our example. So our target region of states is only Q2. So in the first step, we would ask ourselves from which states can we enforce to reach Q2. And this is only Q1 in this case. So actually, your first version of the winning region W would only be the state Q1. Next, your algorithm checks whether the set of all states from which you can enforce to go there is empty or not. So let's see. In this case, if W is only Q1, from which states can we enforce to reach Q1 in the next step? Actually, I would claim that this is no state, because from this state here, the evil guy could just go there. From this state here, the evil guy could just go there. From this state, the evil guy could just go there. So this force would already give us the empty set of states in the first iteration, and your final solution will only be Q1.
Because I have to union the first line with F actually.
Yes, that's a good fix actually. Let's try union F. So now, in the first iteration, we do not only get Q1, but these two states. This is already quite nice. Now you ask yourself the question, from which states can I enforce to go here or here? What we get as a result is Q3. So what you do is you do not abort, but you say the new winning region is the old winning region union Q3. So you really get this circle here. This is also looks nice. Okay, what do we do next? Next we ask ourselves the question, from which states can we enforce to go to these three states. Now this includes Q0, because all the outgoing edges go into this region of states. Actually, when you think of it, it also includes Q3 again, because from Q3 you can ensure that you end up in these three states. And it also includes Q1 again, because from Q1 you can ensure that you end up in one of these three states. It does not include Q2, because from Q2 we will actually fall out. But still, so force of W would give us 0, 1, 3. So previously we had 1, 2, 3. Union with 0, 1, 3 will give us 0, 1, 2, 3, which is perfectly fine. This is actually the winning region we are hoping for. Now what your algorithm does is, again, it computes force of all these states and checks whether this is empty. Unfortunately, this will not be empty, because it includes, for instance, Q0, because from Q0 we can enforce that we go either here or there. So from Q0 we can enforce that we reach this region, so it will also be included. So this force of W will hardly be empty, so your algorithm will most probably not terminate in many cases. Can you think of a way how we can fix this?
Without somewhere, without the W I had before.
Right.
Check if it changes.
Exactly. So what we really would like to know is whether we get any additional states. And So we could write whether force of y, how should I
just
write it?
while the winning rate changes. While we change.
Yes. I was just thinking how I could fix it more closely to this solution. We could say that force y. So if this is a subset of w, then we do not get any new states in the next iteration. So this would be one solution how we could fix this. So if force does not produce any new states, then we can, that we already have in w, then we can stop. Or as you suggest, we can just make this as we had it last week actually, while w changes. So we just monitor the changes of w, and as soon as we do not get any new states, we can stop. Because if we do not get any new states in one iteration, then we will also not get any new states in the next iteration, and in the next iteration, and in the next iteration. So we can just as well stop. Perfect. So this is a very nice algorithm, actually. Let's see what I came up with. So you start with force of F union F. I actually only start with F. But it works just as fine. So what I would do is I just start with Q2, then I ask myself the question, from which other states can I enforce to go there? This will give me Q1, so I add Q1 and have now this region. Then I ask myself the question, from which other states can I enforce to go there? All these states I just include, and so on, and so on, and so on, until I have all the states and I cannot include any more states into my final winning region, and then I'm done. But actually it's pretty much the same algorithm except for initialization. Actually you can also define various other variants of this algorithm. You can even start with the empty set of states and just include F union here, because then in the first iteration you get F, and then for all the following iterations they will just do the same thing, this algorithm and that algorithm, because this F union doesn't hurt, because R is already bigger than F after the first iteration, so this F part here is only relevant for the first iteration, because we initialize our R to the empty set of states instead of F. Actually this looks like a very stupid way of writing it, this looks more elegant, but this one has the advantage that we can actually easily write it as a mu calculus formula. Because remember that our mu calculus formulas always correspond to algorithms that start with the empty set of states and then perform some update as long as some things changes. So here is actually a reminder. So switch off the lights again. So a least fixed point in R for some mu calculus formula phi always corresponds to this algorithm here. Now this algorithm looks pretty much the same as this algorithm, with this formula phi here defined as F union R union force of R. So these mu calculus formulas, you can think of them as compact way of writing down such an algorithm, or you can think of them as formulas describing sets of states as you wish. In any case, there is always this one-to-one correspondence between a mu calculus formula and the corresponding algorithm. So this is one more solution. I even have one more. This solution 3 is quite similar to solution 2. The only thing that I omitted here in solution 3 is the union with R. Now this may look very strange to you, because here it's immediately clear that our set R can only get bigger, 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 because we take the old value of R and wherever we can enforce to go into R in the next step. In this algorithm, this is not so obvious to see that R can only get bigger and bigger and bigger, but my claim is that this solution 2 and solution 3 will always compute exactly the same values for R. We can write this also as a Mühlkalkus formula in quite some compact way. But now I do not want to discuss why these two algorithms always produce the same result. Instead, I leave this as a homework for you. Try to find an explanation why this algorithm 3 and algorithm 2 always produce exactly the same result, and try to explain this somehow in your own words. As kind of a bonus task, you can also try to come up with a formal proof that these two algorithms are equivalent, and whoever manages to do such a formal proof will get one of these Easter eggs next week as an additional motivation.
Can I?
Yes. Okay. Right, there is the Easter break now. So
4 Wochen ungekühlt.
right. Okay. Probably I will have to buy new ones anyway, because if several of you will do a proof, then I only have one Easter egg. It would also be a problem. Okay, but in any case, so this is your homework until in 3 or 4 weeks after the Easter break. Okay, so here is again the algorithm. This is solution 1. Any other solution is also fine. Now, what I would like to do next is discuss how we can compute not only a winning region. So far we just computed the set of states from which we can win, but also a winning strategy. And for that, let's review briefly what this algorithm does. We start with setting the first value of R, which I call R0 here, to distinguish it from the new values of R. And this first value of R we set to F. Then we compute a new value of R, which is the old value of R union the set of OR states from which we can enforce to go into F. In the next iteration, we compute a new value of R by taking all the states that we already had before, and plus we also add all the states from which we can enforce to go into this light blue region, because from this light blue region we already know that we will be able to reach green next, right? And we repeat this, we compute yet another new value of R, which is the old value of R, so this blue box here, union all states from which we can enforce to go to blue. Because whenever we end up in dark blue, then we know that we can go to light blue, and whenever we are in light blue, then we know that we can go to green. So this is how we compute our winning region. So intuitively, Ri are the set of OR states from which we can reach F in at most I steps. So from R0 we can reach F in 0 steps, from R1 we can reach F in 1 step, from R2 we can reach F in 2 steps, and so on. Now the difficult question, how can we turn this insight into a strategy for reaching F? What shall we do in order to reach F if we are in a certain state somewhere here?
We just have to pick all the edges from one region to the inner region, which we can.
Yes. So whenever we are in such a light blue region, but not yet in green, remember that actually all the green states are also part of the light blue region, but whenever we are in the light blue region but not yet in green, we just pick an edge which brings us to green. And whenever we are in blue, then we pick an edge that brings us into light blue. Maybe we are lucky and this edge to light blue is actually an edge to green, maybe not. Doesn't matter. In any case, we get a little bit closer to our goal, and in every step we get a little bit closer, so eventually we must reach our green states. So the general rule, as I just said, is whenever we are in R1 but not yet in R0, go to R0. And actually, why is this always possible? This is also not so easy, maybe?
Because it's always a subset.
Yes. So actually, the difference between R1 and R0 is exactly the set of states that satisfy this force formula here. So all the states that are in R1 but not in R0 must be in force of R0. So these are all the states from which we can enforce to go there. So this is basically why this is always possible. So the intuitive reason is this is just the way how we construct these R's, because we construct them in such a way that this is always possible. Yes, so the general rule is whenever you are in Ri but not yet in Ri-1, go to Ri-1. Now let's try to turn this into an algorithm. So what we do is, while we compute the winning region, we do not only store the final result, but we also store all the intermediate results, all these different R's. Now our algorithm for computing a strategy takes all these different R's, and with the algorithm I use to compute them, R0 is actually our region, our target region. Then we have kind of these onion rings around this target region. We often call these onion rings because if you look at it, it looks like an onion, right? So we have these R's up to a certain maximum R. This is where we stopped to do this, and this maximum R is also our winning region. But for computing the strategy, we also need all these intermediate results. And basically what we do when computing a strategy, here in this algorithm, I just enumerate all the edges that are good in the game graph for winning the game. Initially, I say the set of edges is the empty set of states, but then I add edges to this set of states. What I add is basically for every of these onion rings, I add all the edges where the source state is in some onion ring, Ri, and not yet in the next inner onion ring, and the target state of this edge is in the inner onion ring. So basically this means that from light green without dark green, go to dark green. Take all these edges. But, so this sounds reasonable. What we did not yet think about is what shall we actually do once we have reached the target region. So far we just thought we need to reach it. What do we do after that? Surely we should do something, right? Actually, it doesn't matter what we do because we have already won the game. We can behave completely arbitrary. And this is what this line here says. From all states in R0, these are the states that are in F, so our target states, we can do whatever we want. We pick some outgoing edge. In our strategy thing, we just include all the outgoing edges from states of R0. Then one more thing is, what do we do outside of our winning region? So in this gray part here, which is not part of the winning region, when we start from there, we do not have any hope to win the game. But I'm claiming that we can still get there, namely after we have already won the game. Maybe there are edges from here that only go outside of the winning region. Then we may end up at some point in this gray area. It doesn't matter what we do here, we have already won the game, but still we should do something. So in this algorithm I just said, outside of this winning region, we can also do whatever we want. So this gives us a set of edges in the game graph, and my claim is that if we take only edges that are contained in this strategy, set of edges, then we can never lose the game, basically. Now, initially I said that a strategy is always a function which gives you one outgoing edge per state. This strategy may also give you several outgoing edges per state, but actually any one of these is fine. And in a sense, it is always good to have more options. You will see this in the next lecture. In the next lecture you will learn algorithms that take such a strategy and implement them in a circuit. And if the strategy has more options that are all good for winning the game, then this is good for computing a circuit, because this freedom can be exploited to get small solutions, basically. So this is fine. But how this algorithm actually works, the most important observation we have already made in the picture, right? And you have already said it. If you are in a certain onion ring, try to get closer, 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 closer. This is the basic idea. Here I just wrote it down in some algorithm, just to make it super clear. Okay, so now I think we are actually already done with the first kind of games, and I have never looked at my watch. And this means we should do a break of like 15 minutes, so
11:50.
Hmm?
Till 11:50.
11:15, yes.